I want to welcome all of you to number 18 in our series of seminars on topics in modern physics. And today we're going to talk about science and faith. And I want to begin by telling you that I have an agenda here. And my agenda is not to convince you to believe or to disbelieve any particular set of tenets of any religion, but rather my mission here is to minimize the tension between science and faith. I think they can be compatible. They each have something important to offer, and it's unfortunate in our society that there seem to be people on both sides who would rather fight about it than find common ground. So I'm going to begin, as I often do with my lectures, with quotes by Einstein, because he seems to have said an enormous number of interesting things in his life. And he said, relative to science and faith, that there are only two ways to live your life. One is if nothing is a miracle, and the other is as if everything is a miracle. I think he preferred the latter, being more enjoyable. He also said that all religions, arts, and sciences are branches of the same tree. And he said, science without religion is lame, and religion without science is blind. And I don't think he intended that we should have an argument about whether it's better to be blind or lame. I think his intention here was it's better to have both and have neither of these afflictions. Another quote that I very much enjoy by William Steiger, who happened to be a PhD astrophysicist and also a Jesuit priest and a member of the Vatican Observatory. He said that science and faith are each never-ending quests for the least inadequate description of truth. And I think that that's a very telling statement. And relative to science, it's certainly true. Our theories, we believe, get closer and closer to being a good description of truth. Not everybody would say that they strive to be least inadequate. That's a bit low, but nonetheless, this is a good description of science. And I was happy to hear that he had the same feelings for faith. And I also want to show this. This is the ceiling of the Sistine Chapel, one of the most famous paintings of the Renaissance era. And it was painted by Michelangelo for Pope Julius II, just in the beginning of the 16th century. And the standard interpretation is that God on the right is reaching out to touch the finger of Adam and give him life. But the interesting thing I want to point out is this structure in which God and the angels seem to be embedded. Now, in Renaissance times, up through then, the Catholic Church had been adamant about the protection of human bodies even after death. And it was against the dictates of the Catholic Church to do autopsies or dissections or any such thing on a human body. Nonetheless, doctors and artists did do that in secret. And Michelangelo participated in some of these dissections. And if you look carefully at the outline of this figure, this is almost an exact depiction of a human brain. So you have the various lobes of the brain and the cerebellum down here connecting to the spinal cord.
Good morning.
Good morning.
How are you?
I'm doing good. How about you?
Fine. Thank you. Where's Martha?
Let me just keep that quiet. And then, so the question is, while the Pope wouldn't have recognized this as being the human brain because he'd never seen one, Michelangelo certainly seemed to intend that to be the human brain. And what did he mean by that? Did he, for example, mean that God lived within the human brain? We'll never know, I suppose. Okay, so the outline of today's talk is I'm going to talk about what science is. I am a scientist, and so I can speak about science with some expertise. I'm not a theologian, so I can't speak about religion and faith with any expertise, but I will quote people who are authorities in the field. I'll talk about the strengths and weaknesses of science and an effort to find common ground between science and faith, and end with my ideas about why science and faith can be compatible. Okay, so science is our organized effort to understand nature. And science advances through a combination of data and theory. And by data, I mean any sort of experiment, observation, or measurement of any natural phenomenon, usually which boils down to a number or a picture. And theory is what we think all that means. So it's any interpretation or model or hypothesis that people construct in our own mind to explain the data that we see. And without any good interpretations, science would drown in a series of numbers and get nowhere. But without any data, the theories run wild in all directions, and you never seem to make any progress. So science advances only when there is this positive feedback between data and theory. So how do we decide when we understand the data that we see? How do we know when we've reached a true description of nature? Well, science has no president, it has no pope, it has no Congress or final authority that has the power to declare that a law of nature is true or false. What drives the acceptance of theories in science is the existence of reproducible evidence. So if various groups throughout the world do experiments and come up with the same results, then that gives us a strong feeling, a confidence that those results are in fact correct. And if theories predict things that are measured to be true, then that gives us more confidence that those theories are describing something correctly in nature. And the accumulation of many experiments and many confirmed predictions ultimately leads to a general acceptance of our theories. So the theories that are currently accepted could be characterized as those ideas that our best efforts have not yet proven wrong. So even though we have many theories that scientists cherish, like Einstein's theory of special relativity and quantum mechanics and Maxwell's equations, nonetheless, those theories are being retested almost on a daily basis. As we develop better instruments, those theories get retested. As we come up with new ideas, those theories get retested. And indeed, for a young scientist to get ahead in advance his career, there would be nothing better than to prove Einstein wrong. So people aren't out to prove he's right. They're actually out hoping that they can be the first to prove he's wrong. So if a theory has endured these efforts for in excess of a century in the case of special relativity, then we become more and more convinced that the theory is telling us something valid about nature. So theories lead to predictions, which are tested, which then modify the theories. And through this loop, which can go on forever, we continually improve our understanding of nature. So where does this process work well and where does it work not so well? I'd like you to imagine this country. This is a real circumstance, so I didn't make it up. In this country, the life expectancy is 47 years on average. 8% of the homes in this country have a telephone. 14% have a bathtub. 144 miles of road exist in the entire nation, and only 6% of the adults are high school graduates. So you might wonder what depressed third world country this is. And the answer is, this is the description of the United States in 1904. And clearly we've come a long way from then. And according to economists, the progress that we've made increasing our health and welfare, 75% of that progress is due to science and the technologies based on science, and 25% is due to the return on capital investment. So if you buy a second mule and plow, then you've increased your productivity, which would be the result of investing your capital into a second team. But if you buy a tractor instead, which is based on new technology, then you can do even better. So science generally is the best way that we have developed to address questions whose answers are numbers. Science excels with numbers. So if you want to know the distance to the sun, the age of the oldest rock, the age of the universe, science can provide very precise answers to those questions. If you look at the precision that's involved here, it's really outstanding that we can make measurements that are so precise. So if you want to ask a question that can be answered with a number, science is almost always the best way to do that. By the way, we saw in this slide that the age of the universe is known to be 13.8 billion years with very high precision. This is just over 1% precision. I'm sorry, this is just over 0.1% precision. And there are many people who would like to tell you that the universe isn't 13 billion years old, but it's only 6,000 years old or something like that. And I would like to show you now the simplest presentation I know that is convincingly demonstrating that the universe is much older than 6,000 years. So there was a supernova in 1987, the first observed in the year, so that's A. This is the star that we happen to have a picture of before it went supernova. This is the supernova explosion, which has completely saturated the film in the telescope. It's billion times brighter actually than the star was before it exploded. And the star, before it exploded, had cast off some matter off its outer layers before the final explosion, as is characteristic of these supernova processes. And what happened is this inner ring here, which magnified on the right, the inner ring lit up like a Christmas tree 245 days after the main blast of the supernova. And so what we interpret that as meaning is the supernova blast occurred in the center, and it took 245 days for the light from the blast to reach that dust cloud that was surrounding this ring of dust that was surrounding the supernova. And then that when the supernova blast reached the dust cloud, it lit up. And so we know that the distance between the center of this ring and the edge of the ring is 245 light days, which is a certain distance in kilometers. We know the angle in the sky of that, that this subtends, and by simple trigonometry, we can calculate that this object is 168,000 light years away. which means it took the light of the supernova 168,000 years to travel the distance to Earth to reach our telescopes, which can only happen if the universe is at least 168,000 years old. Anybody have any questions? You know that you can chime in anytime. So science has strengths in various areas, but in other areas, science is much weaker and indeed possibly even useless. So we do not now know and may never be able to answer scientifically why the universe was created, or what is the purpose of human life, if there is one, or what are the principles that we should live by, the ethical principles, or does God exist? And if the answer is yes, which description of God is the one that's closest to the truth? So now let's talk about efforts to find common ground between science and faith. One of the sticking points or areas of contention between science and faith has been labeled by a theologist as the idea of the God of the gaps. So Henry Drummond in the late 19th century was an evangelist, and he came up with this concept of the God of the gaps. He said that human knowledge will always have gaps. There will always be things that humans can't answer. And there's a tendency among certain people to answer those uncertainties by invoking God. One historic example of that is lightning. So for thousands of years, people lived in terror of lightning. We didn't understand it. We didn't know when it would hit. We didn't know where it would hit, but it was devastating. And many cultures, including the ancient Greeks, believed that lightning was the wrath of God. They had statues of Zeus holding lightning bolts in his hand, and he would destroy whatever had made him irate. And that was generally believed, and even into the Middle Ages. It got a little bit confusing when people realized that lightning typically hit the steeples of churches, which were the highest objects in the cities, in the little towns back then. And finally, Benjamin Franklin demonstrated that lightning was actually electricity. It's the electrostatic discharge of static electricity in the clouds. And naturally, it hits the steeples of churches and other tall buildings because that's the least resistive path to discharge the static electricity. So if you simply stick a lightning rod at the top of the steeple, then you can protect your church. The churches were destroyed because they were the least resistive path to discharge the electricity, not because the churches had somehow offended God. So those that invest their faith in this notion of the God of the gaps, that explain everything we don't know with God, will eventually become threatened as science advances and starts to answer some of these questions that were previously unknown. So as this German theologian, Dieter Bonhoeffer, who was arrested by the Nazis because he wouldn't follow their party line, he said from the depth of a Nazi prison that we should try to find God in what we know and not in what we do not know. So this is a advice against believing in the God of the gaps, which would always eventually be a bone of contention between science and faith. Now, in another effort to show common ground, I want to compare the science's theory of the Big Bang with the theory of creation from the book of Genesis. And they both begin with a rather profound statement that there was a time before the universe existed, a time when there was nothing. That in other words, our universe is not eternal going into the past. It had a definite beginning. And the book of Genesis makes the dramatic statement that the universe was created and God said, "Let there be light." And the theory of the Big Bang says the universe came into existence, and the first things that existed were space, time, and energy. And that's a pretty good physics description of light. So there's a direct correspondence here. The book of Genesis describes the creation first of the heavenly firmament, which is the sky with the stars, and followed by dry land, which is the earth and the planets. That's followed by the creation of plants and animals. And that's what science agrees. And finally comes humanity, and that's what science agrees also as well. And then finally, the question is, how long did this take? And in the book of Genesis, it says all of this happened in 6 days. The theory of the Big Bang is it took 13.8 billion years. And yes, the numbers are different. The numbers are very, very different. But I want to ask, if you look at these two descriptions of creation, they are in many ways very, very similar. And and this is striking because these two descriptions come from very different sets of philosophy. They come from very different eras in the development of mankind, and yet they're almost identical except for the number. And so my question is the number the most important part of each of these stories? Scientists would be very committed to the importance of this number. There are others who are very committed to the importance of this number, but the rest of this, we have a remarkable agreement. Okay, so one of the objections people have to science is that it reduces the wonder of our existence. It reduces things to numbers and equations. It's heartless and soulless, and I think that that's an unfair criticism. But it is a view that some definitely have. This is a famous picture. It's taken from the Cassini satellite, which was orbiting Saturn, and from the backside of Saturn, in the shadow of Saturn, the satellite turned its camera to the inner solar system and took a picture of Earth. Earth is the pale blue dot at the tip of the arrow. And it's easy to look at that and think that we're not very important, that we're just a minor speck in the sky. And indeed, the leading astrophysicist of the day said we were nothing but a carbon smudge on an insignificant rock, orbiting a humdrum star in an unremarkable galaxy in some forgotten corner of the universe. And if that was really the position of science, then it would be true that we have managed to destroy the wonder of existence. But I think that that's not the only way to look at science. I think that every time science discovers something more informative about our existence, some new phenomena is finally understood, that only increases the magnificence of our existence. So we have discovered that stars produce not just the energy, but also the atoms that sustain our life. So we are children of the stars. We have discovered how immensely unique the Earth is, or remarkable at least. We've discovered that the universe is extremely finely tuned to enable life. We've discovered some of the myriad workings of the human body, which are incredibly intricate, and that the blueprint of our life is encoded in this structure, which is the most complex that science has ever seen. More people joining us. So briefly, and we've talked about many of these things before, but briefly, when the universe was created at the beginning of the Big Bang, the only nuclei that existed were the nuclei of hydrogen and helium, the red and the yellow, and all of the other atoms on the periodic table, including carbon and oxygen and all the elements that we're made of, were produced by stars. And this is the most difficult process that has occurred in our universe. Through 14 billion years of time and 30 billion trillion stars or more, only about 2% of all the atomic mass in the universe was converted by the stars into the elements that are required for life. So these elements are the most precious ingredients in the universe, and they make up 90% of the mass of a human being and most other living things, and they make up 99.99% of the mass of the Earth. In my various books, I list these 14 reasons that make Earth special to one degree or another. I wouldn't claim that any one of these is absolutely essential to the existence of life, but I will claim that every one of these makes an important contribution to making Earth a habitable planet. And we have data for comparing the Earth's characteristics to the 4,000 other planets that we've discovered orbiting other stars. And we can start to make some statistical analysis with that data set of 4,000 other planets. And we find that we have data for 7 of the 14, and we find that Earth is absolutely remarkably special. Certainly, if you multiply all these odds of another planet matching Earth, you get a number, 1 in a billion or even less. We've talked earlier about the universe being finely tuned, and I like to describe that by saying that the universe has knobs. Obviously, it doesn't have physical knobs, but it has parameters that are adjustable as if they were knobs. And these knobs include the strength of the various forces, the mass and charges, and other characteristics of the fundamental particles and so forth. And some people say there's 37 of these, and some people say more or less, but I think there are 20 that are particularly important. And for each of these knobs, the universe could exist with a wide range of values of these 20 parameters. Each of those 20 parameters could have a wide range of values, and the universe would still comply with all the known laws of physics. But it turns out that if these knobs differed even slightly from the values that we see in our universe, then the universe would not be able to support any form of life whatsoever. So only because each of these 20 knobs is in a very small range of its possible range is the universe able to support life. And science knows quite well what the ranges are. We know with great precision what the knobs are set to in our universe, but we have no explanation for why our universe happens to have those values and not other values. These are called the pillars of creation. These are giant clouds of dust. Each of the pink dots is a brand new star formed by the collapse of these dust clouds. And so this is one of the wondrous sights that we see throughout the universe. But I think the most wondrous sight of all is life. I think even the most humble form of life is much more complex and in some ways much more interesting than even a galaxy. So the question that I've asked is, could life have formed entirely by some random chemical process? And in my view, the crux of that question boils down to the ability to define the code, the recipes for all the processes, all the biological processes that are required to make something alive. And life is extremely complicated. The recipe for all the proteins that are required to sustain life is extremely complicated. And it's all stored in our DNA. So our DNA is the most complex structure that we've found yet in the universe. Human DNA has, this is a twisted helix. The outer rails are like the ladder, and the cross members are like the rungs of the ladder. The cross members are amino acid base pairs, and they spell out a code in a 4-letter alphabet. In the case of human DNA, there are 3.2 billion nucleotide base pairs. So the code in 4 letters is 3.2 billion letters long. And if you were to try to match that randomly by putting together amino acids, you would find that the odds of getting a DNA that matches your DNA would be 1 in a number n, and that number has 1.4 billion digits. Yeah, the number is not 1.4 billion, the number has 1.4 billion digits, which is just unfathomably large. So I would say, no, we're not just a simple carbon smudge on an insignificant rock, ... We are in just the right place, in just the right galaxy, in the right orbit around the right star. We live on the right kind of planet made of the most precious ingredients that the universe has strived to produce over 14 billion years. And the recipe of our life is the most exquisite structure that's been found in the universe. So science has described an existence that is even more magnificent than we knew before. Okay, so I want to make my pitch now that science and faith are compatible. I believe that when practiced by people of goodwill, science and faith are both sincere efforts to seek truth, and truth is something that all people of goodwill will value. These are quotes from 2 luminaries of the Catholic faith, and they are evaluating the knowledge gained by observation, which is the study of nature, and the knowledge gained by revelation, which is the study of scripture. So St. Augustine said that God is the author both of the book of nature and the book of scripture. God created the universe and God created the Bible. So he is the author of all of that. And Pope John Paul II said that the truth cannot contradict the truth. And in his longer version of this quote, he explains that the truth of the book of nature cannot contradict the truth of the book of scripture, since they have the same author. And if humans think that they have found an inconsistency between science and faith, the book of nature and the book of scripture, Pope John Paul II said, then that inconsistency must be due to a failing of human understanding. that we have not completely understood one or the other of the two books, or perhaps both. But the two books cannot be in disagreement, the Pope said, because they're both created by the same author. I want to make note of the fact that in 2009, a poll was published in the LA Times that was conducted by Pew Research, which is a famous polling organization. And they asked US scientists privately, by telephone, I believe, if they believed in a higher power, and 51% of US scientists said yes when asked privately by phone. If they had been asked to stand up in a scientific conference and say they believed in a higher power, then the number would have decreased by about an order of magnitude. So they don't publicly acknowledge this because of peer pressure, I would imagine. Now, some say that some have claimed that science has proven that God does not exist. I think it would be impossible for science to prove that something such as God does not exist, but there are scientists who make that claim, and other scientists who say that science has proven that God is unnecessary. In particular, that claim is made in the last book by Stephen Hawking, called The Grand Design. But I think that science, if anything, leads us to the opposite conclusion. I think almost all scientists would believe that there are billions of planets in the universe. We find in the Milky Way, of all the stars that we are able to examine, that there is on average at least one planet per star. And we know that there are hundreds of billions of stars in the universe. So this is almost a certainty that there are at least billions of planets. And many scientists, most scientists, I would say, would believe that of those billions of billions, there are a great number of planets that would support some form of life. And indeed, some smaller number, but still a great many, would support intelligent forms of life. And as I'll discuss shortly, if that is true, then there must certainly be planets that have intelligent life that is much more advanced than we are on Earth. And let me make that argument. If you imagine taking a human being from 30,000 years BC and bringing them up to the present day and showing them what humans are capable of today, I think they would tremble in awe. We can fly through the air faster than the fastest bird. We build buildings that are so tall you can hardly see the top. We can build bridges across the seas. We can build tunnels under the seas. We can go to the bottom of the ocean. We have gone to the North Pole and the South Pole. We've gone everywhere on the planet. We can take the beating heart out of one person and stick it in another person and have that second person live. We can even walk on the moon. All of these things, a human from 30,000 BC would consider completely miraculous. I mean, they couldn't even conceive how these things could be accomplished. And it would not be at all surprising if they looked at us and said that we were gods, capable of these incredible miracles. And yet we're only 30,000 years further in the evolutionary scale than the humans of ancient times. So look to see, the point I'm trying to make is how enormous has been our progress in only something like 30,000 years, which is about 1% of the period of time over which life has existed on Earth. So by the time life was 99% as old as it is today, we were drawing on cave walls, pictures of bison. And now, we're walking on the moon. So we've made an incredible technological progress in just that last 1% of the evolutionary cycle. So if life exists on some other planet, then the odds of it being more advanced than ours are pretty good. That planet may have started its evolutionary development 1% sooner, or it may have, that evolution may have proceeded at a 1% faster rate. And then that form of life on that planet would be at more advanced by the same factor compared to us as we are compared to these ancient humans. And they would be capable of things that seem miraculous to us, perhaps. I mean, why not? If they are so much more advanced, they could do things that we can't even conceive of. And it would not be completely out of the realm of rationality that some of us would consider them to be gods. Okay, so to conclude, I think that science and faith are both sincere efforts to seek the truth, particularly when practiced by people of goodwill. There are plenty of people of less than goodwill on both sides, but they're not as important as the rest of us. And I like to make the comparison between science and faith to binocular vision. So we have two eyes that view the world from slightly different positions on our head. And so each of those eyes presents our brain with two slightly different perspectives of the world around us. And it is precisely the difference between those two pictures that gives us three-dimensional depth perception. If the two pictures were identical, then we wouldn't have any depth perception. So we see the world in greater richness because our brains intelligently combine two slightly different perspectives on truth. And the analogy I'm trying to make is that science and faith are two different perspectives of truth when practiced by people of goodwill. And if we can intelligently combine those perspectives and take advantage of the differences instead of contesting the differences, then that would be a great benefit to our society. So that's the end of what I wanted to say about science and faith, and we have lots of time for questions. I also wanted to clear up a few things that didn't get answered very well last week. So let's talk about any discussion of science and faith first.
Bob, you never once mentioned the word religion. Please compare and contrast faith and religion.
Well, I think I hesitate to pontificate on theology because I'm completely unqualified to do that. But in my own mind, the distinction I would make between faith and religion is that faith is a belief in a higher power in some nebulous sense, in any sense that one chooses. And religion is an organized belief in a higher power in which there is structure. So for instance, the Catholic Church has a testament. They have a series of beliefs. They have canons and dogmas, and they define a specific way to believe in this higher power. The Jews also believe in a higher power, and they have a different set of beliefs and canons. And the Muslims also believe in a higher power, and they have yet a different set, and the Buddhists and so forth. So there are many different religions. I think there are at least 1,000 recognized religions that exist among humans. But the commonality is that they have a faith. And a faith is something you believe in without what we scientists would say is scientific evidence.
Let me put a finer point on it. Would you say that science and religion are compatible?
Well, I think there's certainly areas where science has a different answer than certain religions. And one can make a big deal out of that. I mean, for instance, was the universe created in 6 days, or was it created, or has all of this taken 14 billion years? Now, I'm a scientist, and are you familiar with Loma Linda University?
I've heard of it.
Yeah. Well, Loma Linda University is founded and organized and run by the Seventh-day Adventists. And the Seventh-day Adventists have told me that they are the most conservative of all Catholic faiths. And about half of their population believes that every word in the Bible is literally true. So for a scientist, this is about as far as religion gets away from science, one might say. Okay, so yet the dean of the School of Religion has invited me to speak at Loma Linda University 4 times, which I did. And they asked me to speak about cosmology and the origin of the universe, and I did. And they asked me to speak about the origin of life, and they asked me to speak about Einstein's theories and so forth, and quantum mechanics. And I presented the most scientifically correct explanations that I could. I made no bones about the fact that the universe was 14 billion years old. That slide that I showed before, comparing the Big Bang and the Book of Genesis, I presented that to them. And at the end, I said, yes, the numbers are different. The 6 days is very different from the 14 billion years. But I said that the message before that was almost exactly the same message. And I thought that that message was more important than the number at the bottom of the page. And I thought that the number was not important enough. The difference in the numbers was not important enough that they should change their faith, the name of their faith, to the 14 billion year Adventists. And at that point, I was not sure whether I was going to be crucified or whether they were going to laugh. But they roared in laughter, and they said that that was one of the funniest things they ever heard. So we were able to have a very intelligent, I mean, these are actually very bright people, very scholarly people. The ones that came to hear my lecture, I obviously didn't meet every one of them. And we were able to have a very nice exchange on these 4 separate occasions. And it's not that I convinced them to denounce their faith, or they convinced me to join their ranks or anything, but we could speak productively together. And, once or twice someone would yell at me from the back of the lecture hall and, denounce me for saying that the world was over more than 6 days old. But by and large, 99% of them thought that it was interesting to hear what science had to say. So, yeah, there are differences, but there are differences between all of us, right? I mean, you became a mathematician, and I still like you.
Robert,
Gil,
I had two different questions. One, regard to the comparing the Big Bang Theory to the book of Genesis. Noted that in Genesis, actually before light is created, I understand that you can't look at the Bible as, you can either look at the Bible as word for word and that it's true or not. But one of the things that it does say in Genesis, it says that before God creates life, that he hovers over the waters. This is before apparently water is created or we have any of the elements created, and didn't see how that sort of fits in. But it does say that in the book of Genesis that God hovers over the waters. And this is before light and heavenly firmament.
okay, I wasn't aware of that. That shows my deficiency in the knowledge of the Old Testament.
Well, mine too. In knowing you were going to look at Genesis, I said, well, let me just take a look at the words, and the Hebrew word is right there, and it says waters. So I couldn't think of any other interpretation of the waters, whatever that means. That's number one. The second thing is that when you have talked about cosmic microwave background radiation and the creation of the Big Bang, and this time period from one tick afterwards to 380,000 years, which is presumably the oldest that we've been able to see by the Hubble telescope. Do you have any idea, at least from a science standpoint or your own personal standpoint, what happened between after the first tick and 380,000 years? Or do we have any semblance of that? What is the truth there?
This one.
Yep.
Okay.
Yep.
Well, we've talked about, we had a seminar about the first 1,000 seconds, and we've had seminars about the theory of inflation and so on. So actually, between the first tick of the clock, if I understand what you mean, and this is a clock which counts in Planck times, which are very short. Between the first tick of the clock, which is the instant of the universe coming into existence, and the era that we're seeing here, which, as you said, is 379,000 years after the beginning. More happened during that period than has happened since, in my view. There are more different phenomena that occurred at the beginning of the universe, indeed in the first 100 seconds, than have occurred since then. So it's an extremely rich and varied set of transitions that the universe went through. And we understand some of those better than others. We have a very good understanding of what happens after 1 second. We have reasonably good projections of things that happened in the first trillionths of a second. And as we get closer and closer to t=0, things get more and more cloudy, more murky, less well understood. So if you have a specific question, I'd like to try to address it, but to address it all would take far more time than we have.
Do you think we're going to have a something beyond the Hubble telescope that's going to tell us something beyond that picture that we see?
Yeah, this actually came from not the Hubble telescope, but a different satellite, but it's a telescope. We're going to have more telescopes. but we cannot have a telescope that collects light that's going to show us an image of the universe earlier than this one, because there was no such thing. So this image comes from the first time that the universe was dominated by neutral atoms that did not absorb light. Prior to that, the universe was this ball of fire, if you will, and a ball of fire is opaque to light, so it doesn't let light through. You can see that if you light a match, you can't see through the flame. Now, if you have a fireplace, you can't see through the flame. And so earlier than this picture, light would have been unable to propagate through the universe. It was immediately absorbed and re-emitted by each atom, and you would not be able to get a picture of that. What we might be able to do in the very distant future is to get a picture using gravitational waves. So gravitational waves are not affected by whether the intervening atoms are charged or neutral. And in principle, we could get gravitational waves emanating from the instant of creation itself. Now, the problem would be that those gravitational waves would have extremely low energy. They would be redshifted by an enormous factor. And it would take technology far beyond our current capabilities to be able to detect something that weak. But it exists. And you know, as our technology advances, one could dream of the day in which we could have a picture of the beginning of the universe.
Thank you.
Robert, I guess something related to that is my question that matter already was formed at 360,000 years, and that was the CMB. Now, before that, there must be the gluons and forming quarks and so on. So when was that? And I was wondering how we can get an idea of that time. That's got to be before 360,000 years.
Yes. Okay.
So what was before then?
Well, we did have a seminar in which we discussed in detail the first 1,000 seconds. And what we said in that seminar was that the particles that we know today, the 17 elementary particles, which include the gluons and they include the quarks that you mentioned, that those particles emerged, we believe, at the end of the era of inflation. So there was something, some form of energy, which has similarities to what we now call dark energy, that drove this period of inflation, which was the exponential expansion of the universe from something extremely small to something of moderate size. And when that period of inflationary expansion ended, the energy that drove that expansion was converted into the particles that we see today. So the time period at which that occurred is estimated to be between 10 to the minus 30 and 10 to the minus 34 seconds after the beginning of time.
So what was then before, during the period of inflation?
That's the era of quantum gravity, which, as we discussed, is the least understood era of the universe. This is now, we're talking before 10 to the minus 36 seconds. And the era of quantum gravity is when, for example, space and time would not be continuous, perhaps. space and time might be, have wormholes connecting from one region to another. It might not be the same number of dimensions. All sorts of things are possibly different. And we will not be able to come up with good ideas about exactly what happened until we're able to come up with a theory of what's called quantum gravity, which would be the unification of general relativity and quantum mechanics. So both of those are great theories, but quantum mechanics works well with minute things, minute energies and minute distances. And general relativity works well with immense things, immense amounts of mass and energy in immense dimensions, immense distances. And the two don't work together. So when you have immense energy in a minute distance, then neither one of these theories really works very well. They tend to come up with answers that are infinity. And infinity is almost always the wrong answer in physics. So we don't have that theory. It's people are working on it. One day, hopefully, they'll resolve these issues, and we can say a bit more about this era of quantum gravity, but not now.
Thank you, Robert.
Okay, can we talk about science and faith? Any more topics on science and faith?
Well, just one comment on what you said is that I think see the big difference too in between science and religion is that all the religions have a prophet, and so all they have all their own doctrines which they follow, and I think everybody can make his own religion, so to say, and
Yeah.
he will have followers.
Yeah. And there are even new religions in recent times, right? And so it's not just something that got it. This isn't all ancient history religion. That there are new religions as well. Yeah, and as I said, I think there have been something like 1,000 different religions that have been identified among different groups of humans. Okay, any other comments on science and faith? I need to address some other issues from last week, but I'd like to finish science and faith first.
I think there's an important issue that you didn't discuss, and that is believing things because an authority says so. That is the essence of the religious approach, not necessarily of the faith-based approach. But it's also true that science has been tainted by that disease.
Well, yeah, I think most religions have an authority, some form of ultimate authority, and the followers are expected to believe what the tenets of the faith are, or they're heretics, which is not a comfortable thing to be.
Heretics have to be killed.
Well, that has certainly happened often, yes. Hopefully nowadays it's not likely to happen as often.
Happening every day.
Well, yeah, but maybe less often. I'm not saying people are good. I'm just clinging to the hope that people are a little better than they used to be.
They're not.
Okay. Well, I think they're better than they were 1,000 years ago or 10,000 years ago. Of course, when we're bad, we can now be bad in big time because we have more weapons to be bad with. But, thousands of years ago, killing another person just for fun was okay. and now it's not okay. So that's progress. I guess my bar for progress is pretty low. Anyway, in science, the heretics aren't killed. If you take a position that's dramatically opposed to the general scientific point of view, various bad things can happen to you, but they're not as severe as what might happen to a heretic. I mean, you would never be burned at the stake for denouncing Einstein or quantum mechanics or something else. You might not get tenure, you might not get research funding. No one might hire you to be a teacher of their university, but at least your life would be safe. So that is a difference between science and some forms of religion, many forms of religion. But, I mean, the Catholic Church has also evolved over time. They used to burn heretics at the stake, and they haven't done that for a few centuries now. So, and the Catholic Church embraces the theory of the Big Bang. In fact, they take partial credit for developing it. With the proviso, the Pope said, that it is understood that it was God that created the universe. So the religions can change. It's they've been, in the case of the Catholic Church, they've been around for 2,000 years. You can't expect them to change overnight. People don't move that fast, but they do evolve. And at least the Catholic Church doesn't want to be in contention with science. They were for a long time, and they've decided that wasn't the best approach.
That was a losing battle.
Yes, that was a battle maybe that they could have won, but the price would have been too high. So the better thing was to be at peace. And I guess that's what I'm looking for, right? It's better to be at peace and to accept some differences as acceptable differences, rather than to say that, I mean, I have members of my family who are scientists who think that there will never be an end to the war between science and faith, that anything a religious person says must be wrong, and that only science is right. I mean, that's an extreme position, and I think it's an unproductive position. I think it's a position that's a losing position.
Professor,
Yes, Shivam.
I want to say one thing,
Yeah.
that the Indian Space Research Organization, ISRO, whenever they start a mission or they launch a spacecraft or something, every scientist just goes to temple and pray to God. And this has happened ever since the ISRO was established. And I think, means I have seen most of the scientists who do the same thing. I mean, before every mission, before everything, they'll just go to the temple and just pray. So I think the graph is pretty high in India.
Okay. So science and religion exist in harmony in India? Is that what you're saying?
Yes, very much.
Oh, well, okay, good.
I bet you that there's a lot of people when they do space launches at NASA that are praying.
I'm sure they are.
In fact, when we were having a course of electricity and magnetism, our professor just said that what God did was, God said, let there be Maxwell equation, and there was light.
Yes. Well, that's a position that the various religions have found productive. not to denounce what science has said, but to say that science is discovering what God has created, right? A religious person can always say, no matter what science discovers, that God created the universe that way, and now you figured it out. Good for you. So the notion that science can eventually defeat religion, that doesn't make sense, in my view. I mean, there are plenty of scientists who are bound and determined to go to their graves, killing as many religious people as they possibly can, not literally, but figuratively. And I think that that's an unfortunate position to take. Unproductive.
Robert, I thought I said this at the Passover Seder. You could consider saying this at the next time at the Seventh-day Adventist lecture you may give. I said I used to be an atheist until I decided, oh my God, nope, I'm not going to be an atheist. There are no holidays.
Yeah, okay. Okay, I'm moving on. So last time, I want to correct a couple issues from last lecture. I had mistyped this equation. So I had I had misplaced the 2's here. I had d squared x, d squared y instead of dx squared dy squared. So that, for the record, that's the right equation. The other thing is, when I looked at the recording of last week's video, I was answering a question from Charlie about fields and the strong force and the weak force. And I pulled up this image from a previous lecture, and I talked about this for about 5 minutes, and none of that appeared in the recording because I hadn't changed the screen share properly. And so for 5 minutes, I was pointing at various parts of picture like this, and all you guys saw was probably some other picture, right? And none of you told me for 5 minutes that I was pointing at something you couldn't see.
I had that problem, I would have said so. I don't think I had that problem.
Did you see this when I was talking to Charlie about fields?
At least I remember this picture.
Well, yeah, because we showed it before, but well, I should ask Charlie. When I was answering your question last week, Charlie, and I was pointing to this various parts of this, did you see this picture, or did you wonder what the crazy thing I was talking about?
I think we had
said
that picture.
Oh, you did, but it didn't end up in the recording. Oh, well, then I don't have to explain it again.
Check on that.
Okay, so one thing I didn't say last week that I should have emphasized, Charlie, you were asking about the fields. You said you were comfortable with the electric field and the gravitational field, and what about the fields of the strong and weak force? And we don't talk about those fields because their range is so short that the field doesn't get out beyond a nucleus. The field's length is, the length of the field extent is only about the size of a proton. So there's no macroscopic field phenomenon that we could measure. So the notion of a field, which was invoked by Faraday to discuss the electromagnetism and retroactively part of Newton's theory of gravity. He didn't express it that way, but retroactively the gravitational field became a concept. We have in modern times abandoned those notions And we no longer talk about the gravitational field or the electromagnetic field. We talk instead, oops, let's see. This is the electric field. This is the electric force. It isn't caused by a field, it's caused by the exchange of a particle. In the case of the electric and magnetic force, the particle that's exchanged is a photon of light. In the case of the weak force, the particle that exchanged is called an intermediate vector boson, which is either the W plus, the W minus, or the Z0. So the notion of fields has been eliminated and replaced by interactions of particles and the exchange of boson particles between fermion particles. The fermions being in green and the bosons being shown in yellow. Okay. Any questions about that or? All right, all right.
Well, are we still allowed to ask questions about that last lecture?
You can ask any question you want now.
Well, very near to that slide that you were just showing, there was a slide that said that because there's n particles in a nucleus, the electric force goes like n squared, and therefore you can't pack more than 92 protons, into the nucleus. And if you could show that slide again and explain it again, I would appreciate it, because afterwards I couldn't really understand beans of that.
Okay, let me see if I can do that. Michael, I have to switch to a different PowerPoint, which means I have to do a better job than I did last week. That was a discussion of forces, wasn't it? Forces. Okay, that's from 2 lectures before.
But, well,
Oh.
in particular, I couldn't understand why the strong force didn't also go like n squared.
Well, maybe I can just say it instead of searching for it. That wasn't the right, it doesn't go, it's not proportional to n squared because not all the protons in the nucleus are have a strong force interaction with all the other protons in the nucleus. They don't because the range of the strong force is short. The range of the strong force can be shorter than this, the diameter of a nucleus.
Okay, that's the
Okay,
answer.
here we are. Okay, now I have to change sharing. Okay. Does everyone see a slide that says physics of nuclei?
Yes.
Okay, good. Well, see, I'm going to learn this Zoom stuff yet. Okay, so Michael is objecting to this, or Michael is asking a question about why is this only a and not a squared, whereas this is z squared. This is, let me explain why this is z squared. First of all, each of the protons is repelling each of the other protons. And so you have z squared combinations. It's z times z minus 1, but anyway, over 2. But it's proportional to the square. So as the nucleus gets bigger and bigger, this total electric repulsion is getting big very fast. It's growing with the square. It's not exactly the square, it's a little less than the square, but it's growing very fast. The attraction due to the strong force is growing less rapidly. And the reason that it's growing less rapidly is that the protons have a strong force attraction only to other protons that are immediately adjacent to them. So in a small nuclei, like let's say helium, all the protons are in contact, both of the protons are in contact with the other one. In carbon, there will be 6 protons and they're all very close, so they all have some level of attraction. But in uranium, there are 92 protons, and each proton is only able to attract maybe 2 or 3 other protons that are immediately adjacent. So the total amount of strong force attraction is growing only about linearly with the number of protons, because each proton, no matter how big the nucleus is, each proton is only able to attract the protons that are in its immediate vicinity. So this is growing more or less linearly. This is growing more or less quadratically. And eventually, this total electric force repulsion becomes greater than the total strong force attraction. So was that okay, Michael, or should I do?
No, I got the picture that the protons only attract the very nearby protons.
Right.
But for the record, for the rest of the people here, afterwards I complained to Bob by email. I want to see how you can calculate that number 92, as I don't have any idea what's the law for the strong attraction, so I can calculate 92. And he said, well, not only can I not calculate 92, but nobody can calculate 92. It's measured.
I still say that. The strong force is does not allow a precise calculation of almost any of its phenomena. The strong force, all of these forces, if you want to calculate the interaction of any of the forces, you end up with a power series that involves the strength of the coupling constant to higher and higher order powers. And it works for the electric force because the strength of the coupling constant is 1 divided by 137. So each term is getting 100 times smaller, so you don't have to add up too many. The coupling constant for the strong force is more than 10. So this perturbative series, it explodes. Somehow or other, the total has to be finite, but we can't do the math right to get a finite answer. So there are approximations that people make and they work to a certain extent, but no one gets a perfect answer to the strong force. Okay, any other questions?
Robert, going back to the problem of barrier penetration, how do you calculate the probability that a particle would penetrate a barrier?
Okay, here you are. Charlie, thank you for asking a question that has to do with the same lecture. Okay, so the probability that a particle will get through the barrier is proportional to the amplitude of this wave squared compared to the amplitude of this wave squared. And the ratio of the two is not very hard to calculate. You have, let's see. Yeah, you have this factor here, which is the exponential decrease in the amplitude of the wave. And so if the height was always determined by a constant A, and if the X was as simple as what I've shown here, then you could just take the product of these two, divide by H bar, and that would be the exponent that determines the rate of decline of the wave function. In reality, it's probably a little more complicated, so you have to integrate the product of A and X, but that's the basic idea. So the higher this barrier is relative to the energy of the particle, the bigger A, and the more rapidly it will decline. And the deeper the barrier is, the more decline you get. And this is calculable. And, you know, for electrons in certain circumstances, you get a significant fraction coming through. And if you're trying to bounce a ping pong ball through a steel plate, the fraction is going to be, you know, 10 to the minus 99 or something. I mean, it's some number that you'll never be able to observe.
So the parameters that you use are X and is this the initial barrier height of V? You need that, you see X here?
Yeah, by X here, I mean the difference between the width of the barrier.
The width of the barrier, right, okay.
The width of the barrier and the height of the barrier above the energy of the particle.
And okay, and the
So
energy of the particle.
So it's basically the area of this rectangle.
Okay. All right, thank you.
Sure. Any other questions? So let me just say that this factor can range over an enormous level. It's, let's see, radioactive decay, where are you? Oh, okay, yeah, here. So this is the same picture with a different barrier, and there are atoms or nuclei that decay in 1/1,000,000 of a trillionth of a second, and there are nuclei that decay in more than 1 trillion years. So there is this huge range which is determined by the height of the barrier, the width of the barrier, and so forth. And the range is huge in large part because this is an exponential function. So it increases, the decrease will be extreme in some cases and modest in others.
Okay, so you cannot tunnel through a black hole then, because the barrier is infinite.
I'm sorry, you cannot do what?
You cannot tunnel through a black hole because the barrier is infinite.
Well, a black hole is a different phenomenon than this one. The black hole does not allow you to get out because the force of gravitational attraction, the acceleration due to gravitational attraction is greater than anything could possibly achieve, including light. We're going to talk about black holes coming up in a few lectures. Okay, anything else? Very good. So this is the end of our third series of lectures, and in 2 weeks we're going to begin the fourth series of lectures. I sent out some information about what lectures I'm proposing to have. This is still based on the the votes that you guys have had over the past. I didn't have a new vote because I haven't caught up with the results of the previous votes yet. So the next lecture will be about nuclear fusion and renewable energy, and what's the prospects for humanity's future means of generating energy. And that's generally all very good news. The lecture after that will be how to measure the distance to remote astronomical objects. So what do we mean? How do we know that a galaxy is 10 billion light years away, and what does that mean? The next will be about wave interference and how wave interference generates all of these really unusual behaviors of nature, like the wake of the boat that we saw, and like the famous two-slit experiment of quantum mechanics. Then seminar number 22 will be about black holes and the phenomenon of small black holes, the phenomenon of supermassive black holes, and what happens with a supermassive black hole in the center of a galaxy and so forth. The lecture number 23 is about quantum entanglement, which is one of the weirdest predictions of quantum mechanics. And the last of the next set of lectures will be about the so-called 10 most beautiful experiments in the history of science. And if someone wants something radically different than that, then I'm open to rearranging it. But these were the items that you guys voted for in the past that we hadn't gotten to yet. So that's why they're on the list.
Professor,
Yes, Siobhan.
I wanted to make a request
Yes.
that whenever you will be teaching quantum entanglement, can you please stress more on mathematics parts of it as well?
Yes. For you, yes. And I'll do that, and particularly in order to torture the others of you who hate math. Well, there's a camp here. This is even worse than religion here. There's a camp here that we have about 3 or 4 mathematicians in the audience, and they get upset if there's not an equation. Or they get upset with every slide that doesn't have an equation. And then there's some of you that are absolutely allergic to math, and you barely have a chance to breathe every time you see an equation. So I tread between the limits. I will not even attempt to convert the non-mathematicians into mathematics. Yes, Jill.
Does entanglement have anything to do with singularity?
No.
Or
We're going to talk about singularities when we talk about black
with
holes.
the black holes? Okay.
Entanglement is
okay.
a different thing.
Yeah. Okay. Sorry. Yeah, I totally got that wrong.
Okay. Entanglement is like a couple dancing the tango, and they never let go.
Okay.
Okay. Thank you all very much for coming, and we'll see you. I hope to see you in 2 weeks.
Thank you, Joan.
Robert.